Let's find the area of the shaded region defined by that equation and that equation. Well, first let's look at the graph they gave us and decide which equation is which. And I'm going to do as much as I can without a calculator, like I try to do, just to gain some calculator fluency. And if you're like, man, I'm not proficient enough in graphing these things to determine what's what, this one's going to be a little more obvious, and you'll see why in just a second. And here we go. Let's just start with the purple pen. R equals 2. That means my radius is 2. So for whatever input of theta you have, wait, I don't have a theta to input. So I have no theta to input, my radius will always be 2. If my radius is always 2, I have a circle with a radius of 2. That would be this one. Which means, by process of elimination, this one would be the other one. So do you have to memorize what this equation does and it makes this shape? And no, don't worry about it right now. Do it in your free time. But it's not a big deal. Okay, so I want to find the area of this shaded region right here. And in order to do so, I need to break this thing up into pieces. So we're going to just start, and we're going to start at 0 radians, which is here, of course. So let's start. Let's go green. Major decisions when I'm doing this thing. So 1/2 from somewhere to somewhere of this function right here. All right, I'm gonna break this up into pieces. Do you remember, say yes, do you remember when we were figuring out the area, how can I word this? The area under a set of curves. If I said, hey, find the area under this little figure right here, then you would be like, oh, well, that's great. That's from 0 to wherever that was. We'll call it A. That'd be the integral from 0 to A of, red. Okay, wait. That has to have a little transition point there. So we'll call that B. Yeah, the alphabet just got messed up. From 0 to B of red, dx, plus the integral from B to A of blue, he wrote in red, dx, okay? I know I'm writing the word blue in red, but here's the deal. The area right here was defined by the function closest to the x-axis, which was red. The area right here, which will truly make blue, was defined by the function closest to the x-axis, which was, well, blue, right? So we had to break this up into 2 separate pieces, and that's what we're going to do here. So I would say which function is closest to the x-axis, but this is not rectangular. This one is which function is closest to the origin as you swing this thing around. So our first piece is this little sector right here. Because once you get past this angle measurement, the function you're dealing with changes to a different function. All right, let's continue this process. It's going to start at 0, and it's going to end here at some theta value. I don't know the theta value at that point. I'm going to find it in just a few minutes. In the meantime, I'm going to move on because I want to go ahead and start filling in my function. This function is the function 2, just 2. So 2 squared, go ahead and put a 4 if you want to, d theta plus. Okay, that takes care of this little sector right here. Now we're going to just keep swinging this thing around until we have another transition of functions. So we did the first one, it's that one. So now we're going to just keep moving, and now we're on the other function. Now the function closest to the origin as we continue to swing around is not the 2, it's the 3 minus 2 sine theta, and that happens until we get to here. Wherever there is, I don't know what that theta value is. I have no clue. We're going to find out in just a minute, though. Theta equals something. And so from this theta value to this theta value, we're going to have another integral. And it's going to be 3 minus 2 sine theta squared d theta plus. Okay. Now we're going to keep swinging this thing around. And as we keep swinging this thing around, we're going to go around this way. And it keeps going and keeps going and keeps going. And the only function that is the closest to the origin at this point is the function 2. So 1/2, and then the integral from somewhere to somewhere, somewhere to somewhere. Let's go ahead and figure out one of those somewheres. We don't know that, but we do know it ends at 2 pi. And the function that defines that one is 2. There it is, just the circle 2. Why I put it in parentheses, don't know. I guess it was just fun. Now, if you want to get technical about it, you could put these two together and just make it a bigger piece of the interval. You can rearrange some things and use some coterminal angles. Coterminal angles are angles that have the same ending ray. Very quick side note here. I could say that this is that. I'm going to go ahead and tell you what it is. This is pi over 6, by the way. The one that we're going to find in just a minute, that's pi over 6. I'll prove it to you, but pi over 6, I can be like, oh, from 0 to pi over 6, and then from this one, which is 5 pi over 6. Trust me, we're going to do it in a second. All the way to 2 pi. Or you could say, I'm going to go from pi over 6 all the way back around to this, but I don't want to call it pi over 6. I could call it 2 pi plus pi over 6, which would be 13 pi over 6. I could totally make an integral that goes from 5 pi over 6 to 13 pi over 6 and do the 1/2 thing and then 2 squared d theta. I can do that instead of having two separate ones. Okay, well now let's back up and find what this is, even though I just told you, and I'm gonna pretend like we don't know. We're gonna switch colors. I'm gonna work it out down here a little bit. I wanna know what angle measurement makes these two radius functions the same. So 2 equals 3 minus 2 sine theta. Let's start moving things around. We're gonna subtract 3. So sine theta is equal to positive 1/2, and then you ask yourself, where is sine positive 1/2? And that answers the question right there. Pi over 6, 5 pi over 6. And now you know, and now we know enough to start filling in these numbers on the interval. So pi over 6, and then this one starts at pi over 6. We're starting here and then swinging around till we get to 5 pi over 6. And then this one starts at 5 pi over 6 and goes all the way to 2 pi. Okay, so we're going to find the final answer, and it's going to happen right now with a calculator. And if you're in the habit of thinking, oh man, this is great, I'm probably going to get some beautiful number that's some multiple of pi, don't get your hopes up, my children. Sorry to disappoint you. 2 squared, let's just go ahead and call it 4, and then d theta, plus, let's just do the whole thing at once. And then 0.5, math 9. I have not entered these in my R functions. If you press y equals, it's not in there. Disappointing, I know. And then I need parentheses around this guy. 3 minus 2 sine theta. All right, another parenthesis around the theta, parenthesis to close the whole function, and then we square it, and then d theta. And then plus 1/2, math 9. 5 pi over 6 to 2 pi, and then 2 squared. There we go. I'm going to proofread it before I press enter. And I'm going to try to do this in my head. You can do this in your head. Well, I'm thinking, hold on, give me a second. Probably about 10, 10.3, 10.4, something like that. Yeah, 10.370. Yeah. Obviously, I already knew the answer because I said it would be disappointing with the whole pi thing. So 10.370, I'm going to divide by pi just for fun, and I get this, which does not turn into a fraction, according to the calculator. All right, that takes care of that one.